Usually when we build something, say like the room you're sitting in right now,
Mm.
there's a pretty firm expectation of visibility.
Oh, for sure.
Yeah, I mean, you can see the drywall, you can point to the wooden studs, the nails holding the frame together. It just makes intrinsic sense to our brains,
Mhm.
because you visually confirm how it all operates.
Right. We inherently trust what we can touch and measure with our own hands.
Exactly. But uh, if you zoom in on reality itself, down to the actual building blocks of the entire universe,
Yeah.
that visibility completely vanishes. Like you, me, the device you are listening to this deep dive on right now, we're living in a world constructed entirely out of invisible materials that are, frankly, mostly made of nothing at all.
It really is the absolute definition of a structural paradox. The very foundation of these tangible objects completely defies our everyday intuition. We're essentially forced to map a reality we can't even see.
And that invisible map is exactly what we're decoding today. We've got a really fascinating stack of sources to work through. There's a foundational scientific guide on atomic structure, and we're pairing that with a highly creative, story-based text. It centers around this place called Nana's Beauty Science Salon.
Which is such a brilliant concept.
It really is. The salon acts as a mnemonic device, like a memory palace, essentially, to help us understand the periodic table. And it also breaks down the precise, rigorous tools scientists use to actually prove how this invisible world works.
Taking these highly complex, honestly kind of sterile chemical concepts and framing them within a relatable environment like a beauty salon, it's a surprisingly effective way to anchor the science.
Definitely.
It allows us to explore the mechanics of reality without getting completely lost in all the abstraction.
So let's just start with the invisible building blocks themselves. The word atom actually translates from ancient Greek to mean undivided. It's the absolute smallest possible unit that any element can be divided down to while still retaining its properties. And to even try to comprehend what we mean by small here, our source text uses a pizza analogy, which I love.
Naturally.
Right. So imagine your favorite pizza. Now imagine taking a knife and slicing that pizza into a billion tiny microscopic pieces.
A billion.
A billion. An atom is still smaller than one of those billion pieces.
It's staggering. And while that illustrates the sheer fractional scale, the source actually gives us a much more mind-bending statistical comparison to really hammer it home.
Oh, right. The one about the human body.
Yeah. If you were to extract every single atom in your own body right now and lay them out in a perfectly straight line, that line wouldn't just like stretch across a room.
No.
It would wrap around the Earth millions of times.
That is just...
Millions of rotations around the globe, just from the atoms making up the body you are currently in.
It fundamentally breaks the human brain to think about scale like that. I mean, it really does. But despite being so impossibly small, the atom isn't just a solid, uniform speck of dust.
Far from it.
Yeah, it's a highly dynamic, organized system with its own anatomy. And this is where the Salon source introduces us to the atom family. They assign these distinct personalities to the subatomic particles. So at the very center of the atom, we have the nucleus, this dense core. And living inside this nucleus are two main characters. First, we have the protons. The source calls the proton the boss.
And the boss moniker is incredibly fitting. The proton completely determines the identity of the atom.
Right, because of the charge.
Well, they do carry a positive electrical charge, yes. But their most critical function is that their absolute number dictates what substance you're actually looking at.
Okay.
So if you have an atom with exactly 1 proton, you have hydrogen. If you have an atom with 79 protons, you have gold. You cannot negotiate with the proton number.
It's hard-coded in.
Exactly. If you add or remove a proton, you literally transform the element into something else entirely. It is the ultimate decider.
So living right next to the boss in the nucleus is the neutron, which the text cleverly dubs the peacekeeper.
The peacekeeper, yes.
Because neutrons have zero electrical charge, right? They're entirely neutral. And if you pause and think about the physics for a second, you realize why a peacekeeper is absolutely mandatory in there.
Because of the repulsion.
Right. If the nucleus is packed full of positively charged protons, and we know positive charges naturally repel each other, a cluster of protons should just, blow itself apart instantly.
They'd fly in opposite directions.
Exactly. So the neutrons sit between them, utilizing the strong nuclear force to bind the whole volatile core together and keep it stable.
Which brings us to the third member of the family, living way outside that tight, stable nucleus, the electrons.
The energizer.
Yes, the Salon story refers to them as the energizer. So electrons carry a negative charge, which perfectly balances the positive charge of the protons. But unlike the protons and neutrons locked in the center, electrons are incredibly fast-moving. They just zoom around the nucleus in very specific orbits.
The shell.
Right, the shells. It is a highly regulated system. Each shell has a strict capacity limit for these energetic electrons. The first shell, the one closest to the nucleus, only has room for 2 electrons.
Okay.
And the second shell can hold 8. Once a shell is full, any additional electrons have to occupy the next shell further out.
And this specific organization dictates how we calculate the mass of the atom, right?
It does. When scientists talk about the mass number of an atom, they are only counting the protons and the neutrons in the core.
So the electrons are just...
Completely ignored in the calculation? Yeah. They're so unimaginably light, their mass is just considered negligible. All the heavy lifting is concentrated precisely in the center.
And this dynamic creates what I think is the craziest fact in our source material. Because the mass is all packed into that tiny central core, and the electrons are zooming around way, way out in those distant shells, the physical distance between the nucleus and the electrons is vast. The result is that atoms are 99.9% empty space.
They're almost entirely a void.
Which, okay, wait. I have to push back on this, or at least clarify it. If you're sitting on a chair right now, you're made of atoms, and that chair is made of atoms.
Right.
And both you and the chair are 99.9% empty space. Logically, you should just phase right through the chair and fall to the floor. The fact that you don't requires some sort of explanation for how these invisible materials actually interact.
It's a very fair point.
To me, the best way to visualize this mechanism is to think about a basic electric desk fan.
Oh, I like this.
When the fan is unplugged and turned off, it's mostly empty air. You can easily poke your finger right through the gaps between the blades.
Sure.
But when you turn that fan on top speed, those blades blur into a solid-looking circle. If you try to push your finger through it now, the sheer speed and energy of the blades will smack your hand away. The fan feels like a solid shield, even though it's still mostly just air.
That is a great analogy. The electrons act just like those spinning fan blades. They are moving at such extraordinary speeds around the nucleus, creating this incredibly dense field of negative charge. So when the atoms in your body get close to the atoms in your chair, those respective negative electron fields interact. And since negative charges repel other negative charges, the fields push forcefully against each other.
So you aren't actually touching the chair at all.
Exactly. You aren't touching it. Your electrons and the chair's electrons are locked in a microscopic electrostatic standoff. It's an electrical pushback, creating the illusion of solid matter.
Wow. So we have this bustling universe of energetic atoms defined entirely by the number of protons acting as the boss in the center.
Right.
But keeping track of every single variation of proton counts requires a deeply organized system.
It does. They don't just float in chaos.
Right. And in the beauty salon story, this is where Nana reveals what she calls the periodic table makeup wall. It's this massive palette, and every single box on that wall represents a different element.
Just to clarify, an element being a pure substance made entirely of only one type of atom. Like a pure block of iron contains nothing but iron atoms, all featuring the exact same proton count. Inside each box on this vast makeup wall, you find the element's unique symbol, its atomic number, which is that all-important proton count, and its name.
The genius of the periodic table isn't just that it lists the elements, though. It's the geometry of how they are arranged.
Yes.
You read it left to right, organized by increasing proton number,
Yeah.
1 proton, 2 protons, 3 protons, and so on. But the layout is carefully structured into horizontal rows, called periods, and vertical columns called groups.
And the vertical groups are really where the true predictive power of the table lies. Elements that sit in the same vertical column share very similar chemical properties. They basically behave alike.
The makeup palette analogy perfectly captures this. Think of a giant professional eyeshadow palette. The manufacturer doesn't just put colors randomly. They group all the warm, fiery terracottas in one section and all the cool, icy blues in another. The periodic table does the exact same thing with physical and chemical personality traits. The most fundamental divide on the table separates the metals from the nonmetals.
Let's look at the physical traits of metals first, which actually make up the vast majority of the table. They share very predictable characteristics. They are shiny, they are malleable, meaning they can be hammered or bent into shape without snapping.
Like aluminum foil.
Exactly. They are also excellent conductors of both heat and electricity, and they typically require immense heat to melt or boil.
Which is why the wiring inside the walls of your home is made of copper, a metal, while the insulating coating around that wire is not.
Precisely.
So nonmetals, sitting on the right side of the table, have the opposite personality. They're typically dull. If they are solid, they are highly brittle and will shatter upon impact. They are poor conductors, acting as insulators, and often have much linear melting and boiling points, meaning many of them are just gases at room temperature.
But the table goes far deeper than just shiny versus dull. The specific vertical groups contain extreme, highly reactive personalities. Take the far left column, for instance, the alkali metals.
Okay.
These are incredibly reactive materials. They desperately want to interact with other substances. If you just expose them to the air, they react almost instantly with oxygen to form a metal oxide coating.
And the sources reveal a really fascinating pattern here. For these alkali metals, as you move down the vertical column, their reactivity actually increases. The elements at the bottom of the group are far more explosive and volatile than the ones at the top.
Correct.
But then, if you swing all the way across the table to a group of nonmetals called the halogens, they're also notoriously reactive. Yet for the halogens, as you move down their vertical column, their reactivity decreases.
Ooh, yeah.
Wait, let's unpack this for a second. Moving down the metal column makes them wilder, but moving down the nonmetal column makes them calmer. On the surface, that feels like a glaring contradiction. If the periodic table is a uniform system, why do these two groups follow opposite rules?
It looks like a contradiction, I know, but it's actually not a flaw, it's a feature. You just have to understand the underlying mechanism of how atoms bond.
Okay, I'm listening.
The entire goal of these reactive elements is to achieve a full outer shell of electrons. Remember those shells we talked about? Atoms are only truly stable when their outermost shell is completely full.
Right.
Alkali metals have exactly one electron in their outermost shell. To become stable, the absolute easiest thing for them to do is just kick that single electron away.
Get rid of it.
Exactly. Now, as you move down the alkali column, the atoms get physically larger. They have more electron shells. That means that single outer electron gets further and further away from the positive pole of the nucleus.
Oh, I see.
Because it's so far away, it's barely holding on. It makes it incredibly easy for the atom to lose it. That is why the larger atoms at the bottom are highly reactive.
It's like they're tossing that outer electron away at the slightest provocation.
Precisely. Now, halogens, on the other hand, are one electron short of a full shell. Their goal isn't to lose an electron. They desperately want to steal one from somewhere else to complete their set.
Okay, so they're pulling in, not pushing away.
Right. And as you move down the halogen column, the atoms again get larger with more shells. But for a halogen trying to pull a new electron in, all those inner shells act like a shield. They block the positive magnetic pull of the nucleus.
No.
The bigger the halogen atom gets, the harder it is to grab a new electron. Therefore, their reactivity decreases as you go down. The periodic table isn't contradicting itself at all. It is flawlessly mapping the inverse physical realities of how different atoms achieve stability.
Wow. That is just a brilliant piece of structural logic. Once you grasp that underlying mechanism, you can look at a blank plate on the periodic table and predict exactly how an undiscovered element will behave.
That's the whole point of the table.
We also have to mention the final column on the far right, the noble gases. In the Salon story, they are referred to as the calm ones. They are completely inert.
Because their outer electron shells are naturally full, they have achieved perfect structural stability entirely on their own. They don't need to steal, share, or throw away electrons. They simply exist, completely unbothered by the chemical chaos happening across the rest of the table.
Just chilling on the side. So we've mapped out this beautifully complex universe of atomic structures and predictable reactivity trends. But humanity didn't just stumble upon these hyper-specific details.
No, definitely not.
We didn't look at a rock and magically deduce its atomic radius or its melting point. How do scientists actually extract this data from reality? The transition from the periodic table to the final room in Nana's salon, the beauty product testing lab, explains the mechanism of discovery.
The scientific method. You cannot build a periodic table without a rigorous, standardized process for isolating variables and testing material properties.
Right.
In the source story, Nana sets up an experiment to test the melting times of different face creams. Now, testing face cream might seem miles away from testing the volatility of an alkali metal, but the framework is identical.
The first step is establishing a research question, which forces focus.
Mm.
You aren't just like observing cream randomly. You ask a highly specific question, like, does the amount of sunlight affect the time taken for cream to melt?
Yes. And next comes the hypothesis. A hypothesis is not an educated guess, people say that, but it's a strictly formatted, testable statement using if, then, because.
The because seems really important there.
It is the most vulnerable and important part of the hypothesis. It forces the scientists to put their underlying logic on trial before the experiment even begins.
Okay.
For the face cream, the hypothesis is, if the cream gets more sunlight, then it will melt faster because it receives more heat energy. You are declaring the exact mechanism you believe is responsible.
And to test that mechanism, you have to lock down the variables. The independent variable is the singular thing you are intentionally changing, in this case, the amount of sunlight hitting the cream. The dependent variable is the data you are measuring to see if an effect occurred, which is the time it takes for the cream to turn to liquid. And then the vital control variables. These are the factors you must keep absolutely identical across every single test to ensure fairness.
Absolutely identical.
You use the same brand of cream, the exact same volume of cream, identical containers, and start at the same room temperature.
Because without strict control variables, the entire experiment collapses. If one sample of cream was larger than the other and it melted slower, you have no idea if it was because of the sunlight or simply because there was more mass to melt. You haven't isolated the cause.
After running the method, scientists don't just record the result and publish a textbook. They repeat the experiment over and over. They do this to calculate an average, but primarily to hunt for what the text calls an anomalous result.
The anomalies are key.
Right? Like if 2 samples of cream melt in 5 minutes and the third takes 45 minutes, that massive spike is an anomaly. It signals that a variable wasn't controlled properly or some unknown factor interfered. Finally, you write a conclusion mathematically evaluating the hypothesis, followed by an evaluation of the experiment itself. Did the methodology work? Should we have used a digital thermometer instead of relying on the thermostat?
The scientific method is essentially a standardized machine designed to eliminate human bias. It forces you to construct a scenario where reality can clearly tell you that you are wrong.
So it's basically a highly structured recipe for catching your own mistakes. But if we look closely at this idea of control variables, a glaring issue comes up for me, especially outside of a billion-dollar sterile laboratory.
Oh.
Yeah, if you were testing materials in a beauty salon or a high school classroom or out in the field, it is virtually impossible to keep absolutely everything identical. There might be a slight draft hitting one beaker. A cloud might pass over the sun, altering the ambient light for 30 seconds. Human reflexes on a stopwatch are inherently flawed. If the messy real world is that unpredictable, is a perfectly fair test ever actually achievable?
I love this pushback. In the absolute strictest sense, no. The real world is incredibly noisy. Minute, uncontrollable variations are always going to seep into the data.
Right.
But that is the precise reason the repetition and evaluation steps are non-negotiable. Science does not require a single instance of flawless perfection.
It doesn't.
No. By repeating an experiment hundreds or thousands of times, the chaotic noise of the real world mathematically averages out. That slight draft in the room, the human delay on the stopwatch, those anomalies flatten out over a large enough data set. What remains, rising above the noise, is the true underlying physical pattern. The method extracts truth through volume and statistical averaging.
That's incredible. But the method doesn't demand a perfect world. It just provides a mathematical lens to filter out the imperfection.
Exactly.
Think about what that means for you as you go about your day. Every piece of technology you rely on, the materials constructing your home, the medicine in your cabinet, every single one of those elements had its properties extracted from the noise of reality using this exact framework. The invisible atoms we discussed, which make up 99.9% empty space, organize themselves into the predictable categories of the periodic table, and we only know how to harness them because generations of scientists relentlessly applied the if-then-because logic of the scientific method.
It completely reframes how you view your physical surroundings. And, the atomic structure source leaves us with one final, deeply profound visual.
Yeah.
It points out that atoms themselves are never destroyed. They cannot be eradicated. They are simply recycled and rearranged endlessly. The atoms operating inside you right now have been here since the formation of the planet.
The building blocks are eternal.
Yes. The text traces the hypothetical journey of a single atom. It might have spent millions of years making up the bone density of a dinosaur. then eventually scattered into the soil, absorbed by a crop, consumed by a monarch butterfly, exhaled into the atmosphere, breathed in by Albert Einstein, and eventually found its way into the cellular structure of your own heart.
That gives me chills.
When you understand the atomic anatomy and the undeniable physics holding it all together, you really have to wonder about the past lives of the invisible materials you are currently borrowing and, where they will go to be tested next.
That is something to think about. And that wraps up our deep dive for today. Keep wondering about the invisible world around you, and we'll catch you next time.